So, hello everyone. Welcome back again to our GR school. So today we have Hassaan Saleem. He'll be giving four lectures in this GR school. So a bit about him. He did his undergrad and master's from University of Punjab, and then he did another master's from ICTP, and now he is a PhD student at SUNY Albany in New York, United States. And he works on a variety of things. Conformal field theories. He's interested in string compactifications as well. Also, more amazingly, he has this uh, science SciComm channel on YouTube and Twitter, which is promoting science, which is very nice and very helpful for everyone. So he's a great science communicator as well, that I should mention. So we are very lucky to have him here, and I'll pass the mic to Hassan.
Thanks for the kind introduction. Okay, so we're going to start this lecture by talking about one of the ingredients that you will need to construct Einstein's field equation, right? So if I write down the schematic form, right, for the Einstein field equation, Einstein's field equation will try to connect geometry of space-time with matter present in space-time, right? So if I write a schematic form for Einstein's field equation, it should be something like this, like geometry side, whatever it is, equals matter side, right? So in the previous lectures, you have pretty much covered what comes on the geometry side, right? In this lecture, we will try to cover what can come on the matter side, right? But before I go into that, go into the telling you that what comes on the matter side, I need to address one thing. So in Newton's gravity, what happens is that mass is the only source of gravity. So if you write down Newton's formula for gravity, it's something like this, right? You see that only masses appear here. So these two things are masses. But in general relativity, mass is not the only thing that's the source of gravity. It's actually much more complicated than that. It will turn out that energy and momentum are also sources of gravity. And I'll sketch a small argument for you to convince you that energy and not mass is the source of gravity, right? So suppose that you have a box like this with a partition in between. And in the upper side, you have like some positively charged particles. And in the lower half, you have their antiparticles, right? Which are negatively charged. I mean, the charge doesn't matter. The only thing that matters is that these particles are antiparticles of each other, right? Now, they will have mass, right? Now, suppose that there is some object here at rest, right? Now, this whole thing has mass m, for example, right? Now, this thing will attract this object towards them, right? And you can say that, okay, this attraction is happening because of the mass, right? Because that's what Newton's gravity tells you, right? Now, it will accelerate this particular object. Let's call it object A, right? So it will accelerate A towards itself, right? And after it has gained some speed, like speed v, for example, we we will remove this partition, right? If we remove this partition, what happens is that these particles and antiparticles annihilate each other, and you get pure photons. Like, I mean, I'm using the word gamma, alphabet gamma, because gamma is used for photons, right? So we do know that when particles and antiparticles, interact, they annihilate each other to give you photons, right? Okay. Now the thing is that this object has gained some speed, called v, which means that it also has some kinetic energy. Now, photons don't have mass, but they do have energy. But if gravity was created by only mass, then what happens is that after you get photons, any gravitational potential energy that you would have between this object A and the particles and antiparticles will just vanish now because now you don't have any mass. But if that's the case, you can see that in the start, you had object A here and, the box here, and you had some gravitational potential energy. Let's call it V or V1. And the kinetic energy was zero because this object was at rest. So the initial energy was V1 plus K1. And you have to remember that gravitational potential energy is negative, right? After it had gained a speed, well, V, there is some kinetic energy that's K2. Now, the thing is that K1 is actually zero, so I don't even need to write that actually. So K2 is the new kinetic energy, and the new potential energy is V2 plus V2, right? Now, the thing is that these should be equal because energy is conserved. But now, if you have photons here, this V2 should just vanish if gravity is generated by mass only, right? So this should vanish. But now you have a problem. You have a problem because this equation should be correct, but that can't be true because this side is negative. As I told you, that gravitational potential energy is negative, but the kinetic energy is positive, right? So it's a small argument to show that mass cannot be the only thing that generates gravity. How to solve this paradox? Well, you can solve this paradox by saying that gravity is also generated by energy. And then you don't have a problem because then this contribution doesn't have to go away, this V2, because photons still have energy, even if they don't have mass, right? So then you will have this term here and you don't have this problem, right? Okay, so this is a small argument to show that gravity cannot be generated by mass only. It should also be generated by energy. And we will see later that it should also be generated by momentum. Okay, okay. Now let's talk about an object that you will need to construct Einstein's field equation, and that object is called stress tensor, or sometimes stress energy tensor. Some people call it stress energy momentum tensor, but we will just call it stress tensor or stress energy. I think that's better. Now, the stress energy tensor depends on what kind of entity you're talking about, right? So we will start from a very simple entity that's used in GR, and it is called dust. Now, how do you define dust? Well, you define dust by the following definition. So dust is composed of particles. So composed of particles that have no interaction with each other. And the second thing is important. Around any given event, those particles are at rest relative to each other. Right? So this is the technical definition of dust. I mean, dust is a word that we use in our daily lives, but this is, that the meaning that we have in our daily lives is not the meaning that we are using here, right? So it's a very, technical term that you need to have particles that don't move relative to each other around any given event, and they don't have any interactions, right? So it's a very simple object if you, try to think about it. Now, how do you, calculate the energy density of this, object called dust? Well, it's actually pretty simple. So if you look at a reference frame, I'll make a cube for this, right? Suppose that it has some dust particles in it. right? Suppose that I have n dust particles in it, and each particle has mass m. So n particles of mass m, right? And they are in a cube of length L, capital L, right? Now, this is the frame in which the dust particles are at rest. Sure. Now, if I talk about the energy density that they have, or the mass density, whatever, I will call that rho naught. Now, this is rho. And naught means that this is in the rest frame. Well, this is simply n times m divided by L cubed. Now, n is the number of particles, m is the mass of a single particle. So n times m is the total mass or total energy, because C is 1, so mass and energy are the same thing. So n times m is the total energy divided by volume, which is L cubed. Okay, so is that it? Well, that's in the rest frame. We need to see how this particular quantity transforms if we go into a different if we go into a different frame. So suppose that we watch this same box in a frame in which it is moving in the x direction. Okay. So suppose that this box has like velocity v in the x direction. Now, if that's the case, then we do know that we have length contraction, and this length will become L over gamma. Now, if you remember, gamma is just 1 over v square over c square square root. But since c is 1, so we will just take it to be this thing. So whenever I write gamma, it means this quantity. And I'm pretty sure you know that length contraction happens by this vector. Okay. Now, the other lengths are not changed. This length is not changed, and this length is not changed, which means that the total volume, so new volume, is just L cubed divided by gamma. But is that the only thing that changes if you have, this speed v here? Well, that's not it actually, because the mass of a single, the energy of a single particle, not the mass, energy of a single particle will also change because now they are moving in this frame. So energy of a particle is now gamma times m. If you know this formula, E equals gamma times m naught c squared, you will know, and c is 1, so just ignore c. So this is the energy of a particle moving with some speed v, and s just the rest mass of the particle. So the new energy of a single particle is this. So in this frame, what is the energy density? Well, I will call the energy density rho now, not naught, because naught means that you are in the rest frame. So rho is the energy of all the particles. Now n times gamma m. The number of particles hasn't changed, so n is invariant, divided by the new volume, and the new volume is this, right? But that's just gamma squared times the previous thing that we had, and that's just this thing, right? Because if you remember, rho naught was equal to this. Okay. Now, let me remind you what for velocity looks like. So, for position is defined like this, right? For velocity, which is denoted as u, and this is mu. Let me use alpha to not confuse mu with mu. That is defined like this. Please let me know if you don't understand any notation that I'm using. I can't promise that my notation will be the same as the notation of the previous lecturers. So this tau is proper time. Okay. Now the thing is that this for velocity that I have written here, this is nothing but gamma. You can easily see that because of the time dilation formula. This is the time dilation formula, right? Well, what about the other things? Well, this is just gamma times the velocity vector, right? Uh, how can you see that? Well, that's pretty simple. You just write it like this. This is gamma, and this is the velocity vector, right? Now, if you look at this thing, that gamma is just, dt over d tau, you can also write this as the time component of the forward velocity. Then you can see that this rho that I wrote earlier, rho was gamma squared rho naught. You can write it like this: rho naught times ut times ut, which is, I mean, it's pretty self-evident because ut is just gamma, right? So ut means the time component of, the floor velocity. Now, this energy density that I'm referring to, rho here, I will call that TT. I'll explain why I'm doing that in some minutes. Now, what is this capital T? This capital T is called the stress tensor or the stress energy tensor. And TT means that it is the time component of the stress energy tensor, right? If I generalize it, this expression to a full tensor expression, it will give me something like this: T mu nu equals rho naught times mu, or let me use alpha beta, alpha and mu beta. And this is the formula for the stress tensor for dust, right? I started with only the time component. What about the other components? Well, we'll see what is the meaning of the other components. But let me write down the whole expression for the stress tensor now. So you can see that it has a time component. It has a time x component, time y component, time z component, and then x time component, y time component, z time component, and so on. And you can see the um, pattern now. Sorry, x, y, 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 z. Well, zx, zy, and zz. But I can summarize it like this. It has four different types of components. Time component that I will also refer to as 0, 0, because time component is referred to as the 0th coordinate. These are time and then a space component. I means that it's the space component. It can be x, y, or z, or one, yeah, or 1, 2, and 3. These are I0 and these are ij, right? So this is the division that I made. Okay. Now, what about the meanings of these components? Well, the T00 component is just the time component. And we saw earlier that the time component is just the, it's just actually rho, and rho is nothing but the energy density, right? So we don't need to explain the meaning of that, at least. What about the other components? What about this component, and this component? Well, let's see the meaning of these. So let's start with, for example, the time x component, right? What is the meaning of that? Well, if I use the definition, I get this ut ux, because that's the definition that I had here. Okay. Well, if I use the meanings of these components that I wrote earlier, so I told you that the time component of u is just gamma, and the space components are gamma times the velocity vector. Okay, so this means that this is rho naught. So rho naught times gamma times Vx. Well, that's just gamma squared, right? And gamma squared. And this is nothing but rho, right? By rho, I mean energy density in a different reference frame. I mean, rho naught is the energy density in the rest frame only. So we derived that here, if you remember here. So rho is equal to this thing. Okay. So that just becomes rho times Vx. Now, imagine that you have an area A, let's call it area A, and dust is moving in x direction, or it can move in any direction actually, but it has an x component of velocity. So x. But in time delta t, it will cover a distance. In time delta t, it will cover a distance Vx times delta t, right? So if I multiply the numerator and the denominator by this thing, what will I get? Well, what is the numerator? What does the numerator mean? Well, rho is just the energy density, right? Vx times t is this distance, right? And area is this area, right? So it means that this whole thing just means energy density times the volume of this cube that I have made here, right? That means that the numerator is just the energy contained in in this cube because it's density times volume. So it's energy contained in the cube. What about the denominator? Well, denominator is simple. It's just area times time. So it's area times time, right? Now, it means that the Tx component of the stress tensor is just energy per unit area per unit time. But that's nothing but energy flux, right? Flux is defined, flux of a quantity is defined as that quantity per unit area per unit time, okay? So this is also called energy flux. But since, we only considered x direction, so this is energy flux in x direction. And you can easily see that you can use this argument to show that this component means energy flux in ith direction. I can be x, y, or z. Okay. Okay. What about another interpretation? Now, if you take the same equation that I had here and multiply in the numerator and the denominator with Vx, well, it doesn't make any difference, right? But now you can see that the numerator and denominator have changed, which means that the meanings of these things will change. So in the denominator, well, as I argued earlier, that this is just the volume of this cube that I made here. So this is volume, right? But now this Vx that I multiplied here, let me write it down in a different way. Let me write it down here, Vxa delta t. Now this is still the volume, right? But what is this? This is not the energy density anymore. Well, if I write down the for momentum is energy and momentum, right? It means that momentum, if you remember the formula for momentum from special relativity, it is m times the formula for, m times v divided by 1 minus v squared, which is nothing but this thing, but this is nothing but energy times v, right? So it means that if you have energy density times velocity, that's momentum density because momentum is energy times velocity. So this is a momentum, x momentum density actually, x momentum density, sorry. So this is x momentum density. This is just volume and you are just dividing by volume. So this, you can even cancel this if you want. So then you don't have to do all this. So this is just x momentum density, right? So now you have a different interpretation. It means that I don't need this anymore. It means that this T0I component can mean energy flux in the ith direction, but it can also mean ith momentum density. So you have two different meanings attached to the same component. And you using the same kind of arguments, you can show that Tij means, now this 0 indicates that you are talking about energy. That's why energy comes here. This 1 indicates that you are talking about ith momentum. If you repeat this argument that I just did with Tij, you will find that this is ith momentum flux in jth direction, right? So it means that if you write T ij, this component tells you that which momentum has the flux. So ith momentum flux, and this tells you that in which direction the flux is in. So in which direction the flux is in jth direction, right? So this is the meaning of the components of stress energy tensor. Another thing that you may have noticed earlier is the following. If I write down the expression for the stress tensor, it's rho naught times this, right? Let me use alpha beta, I'm sorry, alpha beta. You can see that if I write beta alpha, that becomes this, but that's not different than this. You can just, write them down in a different order. That's not a problem, but that's just alpha beta. It means that for the dust stress tensor, this is the case, which means that you have a symmetric stress tensor. Now, I have used the formula for the stress tensor of dust to show that you have symmetry in the indices, but this is a very general property of the stress tensor. I mean, for any quantity, and sorry, for any entity that you can write down the stress tensor for, it should be symmetric, and there are many reasons to to require that stress tensor is symmetric. Okay. Uh, do we have any questions before I move on? Okay, but by the way, I don't know if I will need to read the questions or will you tell me the questions?
I suggest just sporadically checking the chat, basically, and then you can
Okay,
just answer them.
sure. Uh, right. Okay. Can you not erase? Okay, I can try not to erase. Yeah, that's one of my habits. I can do that. Okay, are you able to listen to me? Because some people are saying that the sound is not coming across well.
Me, yes, I can listen to you pretty clearly, and
Okay, good.
I don't know why some people are having this problem. Maybe it's a glitch.
It's probably okay. Uh, dust doesn't have interactions. Yes, dust doesn't have interactions. It's very important that dust doesn't have interactions because otherwise you will need to incorporate their potential energy. And I have not done that. So yeah, dust doesn't have interactions. Okay. Some people were talking about negative mass. No, no. When I said that, you have positively charged and negatively charged particles, I meant the electrical charge. It has nothing to do with mass, right? I did that to show that these particles are just antiparticles of each other. The charge doesn't matter really. The only fact that matters is that when they annihilate, they give you photons. That's it. Okay. Okay, let's proceed then. Uh, okay. Now I need to derive a property of the stress tensor. Wait, I think we have another question. Uh, U alpha and U beta commute. Yes, because they are just vector components. There is no reason why they shouldn't commute, right? If they were fermions, I don't know if you are familiar with fermions. If they were fermions, then yeah, they won't commute. But here they are just components of a vector. So yeah, they commute. Okay. Now I need to derive a property of the stress tensor, which will be very important to derive Einstein's field equations. Okay. And if I, uh, yeah, okay, I think I can do it later, but let's start to derive that property. So let me make a big cube for this. And let me know if you don't understand the notation that I'm going to use, because it's a possibility that some people may have some problem with the notation. Oh, sorry. Okay. Now, what I'm going to do is to derive something called the conservation law of stress energy tensor. And for that, I have made this cube. Now, the thing is that the midpoint of this cube has coordinates x, y, z. Well, yeah, x, y, z. right? And this, well, let me show you what directions the coordinates have, like these, like X, Y, and Z, right? Now this face, let me color it. This face has coordinates. Well, Y and Z coordinates change on this face, but the X coordinate is X minus delta X over 2. This face, this face has coordinates X plus delta X over 2. And this whole length is delta X. This whole length is delta Z. And sorry, that's delta Y. And this length is delta Z. Okay. Now, what I'm going to do is that I'm going to write down, calculate all the energy that's coming in into this cube, and I'm going to equate that into the change of energy, change in energy that you have in the cube, right? So I'm going to raise these because they will be a problem later. But you know what I'm doing here, right? Okay. Now, if I ask you that what is the energy that comes in through, let me erase this. Yeah. What is the energy that comes in through the shaded cube? Well, it equals the energy density at X equals this thing, right? Multiplied by the area of this face. Sorry, not energy density, energy flux times area times time. So what is the energy flux? Well, energy flux, as we discussed earlier, was just Tx, or I will write T01 now because that's the notation that we use, times area of this face, which is delta y, delta z, multiplied by time. It will take some time for it to reach this central point. Okay. And now let me choose a different color. Let me shade this face as red. What is the energy that goes out? Well, let me erase this. I think I need extra space for this. 1 minute. So this is T01 at X minus delta X over 2 Y Z multiplied by delta Y and delta Z and delta T. And same thing here, but now it is T01 del X plus delta X over 2 because it's at this face, and Y Z and same thing, right? Okay, so that's the energy that goes out of this space. You can do the same thing for, yeah, it's going to be a bit cumbersome. You can do it for this, sorry. You can do the same thing for this forward face and the backward face and the, face above and the face down, right? And you will get similar expressions. But let me just do this, do the procedure for X direction, and the same procedure holds for Y direction and Z direction. So energy change equals, now this is bringing in energy, okay? Which means that it's a positive change. So it is equal to T01 X minus delta X over 2 Y Z times delta Y delta Z delta T. This is a negative change because it's taking energy out, okay? So you have to subtract this. Right? And this factor is common, so let me just take it as common. So this thing multiplied by delta Y, delta Z, and delta T. Okay, so you will have similar contributions for, faces which are perpendicular to Y direction, which are, front and back, and faces which are perpendicular to Z direction, which are, up and down. So if you include those contributions, the faces that are perpendicular to the Y direction will be, T02. And now the Y direction will have a change. Minus X, I'm sorry, X, Y plus delta Y over 2, Z. And here you can see that there is no delta X because that's the direction in which, that's the direction perpendicular to the face. So here you will not have delta Y. And for the z direction, you will have the last contribution. Sorry. So that's the whole energy change, okay? Now, this whole energy influx and outflux that you're having, for this box, that will change the energy in the box, right? Okay, but what is that change itself? Well, I think I should not write energy change. Influx, well, energy brought in or brought out. Or, yeah, I think brought in. That's a better way to write this. So what is the energy change? Well, that's actually pretty simple to write because before time delta t, the energy is T00. So you remember T00 is the energy density, okay? So T00 at x, y, z, but at time t, that's before time. So yeah, that's the initial energy. Yeah. The final energy density is, well, I don't even need to write x, y, z actually. Just write time because x, y, z are constant. The time t plus delta t. So this is energy density, which means that you need to multiply this with respect with the volume, which is delta x, delta y, delta z. Now, energy brought in should be equal to the energy change. Okay. It's so a question is that why t's first component is always zero? It's because we're talking about energy, right? You can do the same argument for x momentum brought in and change in x momentum. Then the first component will always be one, right? You can do the same argument with y component of momentum brought in and the change in y component of momentum, and that then the first component will always be two, and so on, right? Since I'm talking about energy, that's why the first component is always zero in this calculation. Okay. Okay, so these two things should be equal. So if I equate them and divide both sides by delta x, delta y, delta z, delta t, if I do that, then this energy brought inside becomes divided by delta t, because these will be cancelled when I divide by delta x, delta y, delta z, delta t, right? And the other side, so this side, let me just write down this x term, and the y term and z term will be similar. So the x term is delta 0, 1, x minus delta x over 2. Y and z are constant, so I'm not even writing them, just to, avoid the clutter. Divided by delta x, because that's the only thing that will come here. These three terms will cancel, right? When I divide by delta x, delta y, delta z, and delta t. And similar terms for y and z. I will write those terms, but let me just process these two terms first. Now, what is this? Well, in the limit when delta x, delta y, delta z, and delta t all go to 0, this becomes, this thing becomes partial 0, 0 over partial t, or partial, partial t. Yeah, okay. What is this? Well, this becomes partial t01 divided by partial x, but with the negative sign. Why? Because this term is coming first. When you define a derivative, the x plus delta x term comes first, then x minus delta divided by 2 thing comes later. But this has x plus delta x over 2 term after the minus sign. Therefore, you get this minus sign in the derivative. Okay. Okay. So the y term will be similar. It will be minus 2, this thing divided by y, or in other words, x1. I can write this x0. I can write this x2. And this z term will become this thing. So the equation that you're getting is this. Minus But you can simplify this equation very simply, actually. You can bring everything on the left-hand side, and then you can write this equation as follows, right? So this mu covers, time and space components. And a better way to write this equation is this. Now, this equation is called the continuity equation for energy, right? It's continuity equation because it tells you that if there's any change in energy in a given region, that change in energy has to come from the boundaries of that region. And that's exactly what we did in this calculation. Now, since we did it for energy, that's why, I mean, as one of the people asked, this component is always zero because we're talking about energy. We can do the same calculation for the x component of the momentum, y component of the momentum, and z component of the momentum, and then you will have this component equal to 1, 2, and 3, which means that that this equation is true, but doesn't matter what this component is, right? So it means that the general form of this equation is this. And this equation is referred to as the continuity equation for T mu nu. It's also referred to as the conservation law of T mu nu because that's what this equation is doing, right? It's telling you that any energy coming in a region should come from its boundaries. That's like local conservation. Okay, this equation is actually very important when we will go to, developing Einstein's field equations. Okay, so does anyone have any questions regarding this calculation? Oh yeah, one of the questions is about flat space. That's a very good question. You're correct. This equation is true locally if you talk about local coordinates, right? But we will write down the general form of this equation in a minute. So the thing is that, as you pointed out, that this equation is true only if you have if you have flat space time. Well, I'm pretty sure you know about a local inertial frames, which means that at any given point, you can always choose a metric that is flat and it has first derivatives equal to 0. And in that particular coordinate system, this equation is true, but it's not true in general, coordinate systems. So in general or arbitrary coordinate systems, this equation will become something like this. So the derivative that we had is replaced by covariant derivative. Because the thing is that this equation itself is not covariant because it has a derivative. But this equation is covariant. It will have the same form in all coordinate systems. So yeah, that's a good point. I was going to come to that in some minutes. Okay. Any other question? What is the physical significance of this equation? It tells you, I mean, as I said earlier, that if you have a region, any change in energy in that region should come from the boundaries. So energy must leave the boundaries of that region or come through the boundaries of that region. So it kind of, the thing is that if you say that energy is conserved in this universe, right? Suppose that there is some energy that's present here. If it vanishes and, at the same time it appears in Andromeda galaxy, for example, instantly, that will not violate the conservation of energy, right? Energy is still conserved, but um, that will violate the local conservation of energy, which means that if some energy has gone from here to like Andromeda galaxy, it has to go through the space between these 2 points. So this particular equation that I have written down, it tells you that energy is locally conserved. If any energy leaves, a region, it has to go through the boundaries of that region. So that's this physical significance of this equation. Yes, I have changed the covariant derivative to Kurt's space. Yes. Okay, let's move on. I have a lot to cover, so I don't know how much time I have. Okay. Now, in order to proceed, I will talk about another, um, kind of entity. And that new entity is called the perfect fluid. Now, perfect fluid is a bit more complicated than dust, but it's still pretty simple. So perfect fluid means that you have random motions. Well, first of all, still non-interacting. I mean, particles still don't interact. But in dust, I told you that, around any given event, particles of dust are at rest to each other. That's not true in perfect fluid. In perfect fluid, particles can have relative motion with respect to each other, but those motions are just random, right? So these two things are important. Random, random relative motion, yeah. And this random thing is very important actually, because one of the derivations that we will do, I hope that we have time for that. Yeah, that will involve the fact that the motions have to be random. Okay. Now I'm going to claim that the stress tensor for this perfect fluid is this, rho naught. And now you have a new quantity. Sorry, let me write it in the matrix form first. So rho naught, 0, 0, 0. Now you have a new quantity called the pressure. And that was not true in, in the case of dust, for example, right? So for perfect fluid, how does this pressure come about? We will discuss that. For comparison, if I remind you what was the expression for, for dust, it was this thing, right? In the rest frame of dust, it just becomes rho naught, and these become like mu zero, mu zero. Because if you look at the um, 4 velocity, which is this thing, right? In the rest frame, the 4 velocity just becomes this, right? Which means that you have a non-zero contribution only if you have, the zeroth component. So you can write down the stress tensor for dust in the rest frame as this. So a rest frame of dust, right? If you compare this stress tensor with this stress tensor, the only big difference is that you have pressure in the case of perfect fluid. We have a question which says that why is this matrix diagonal? Yes. So when we will derive, this stress tensor, there is an argument to show that this has to be diagonal. It has to do with an integral. We'll come to that. Okay. So this was just for comparison, so I don't need that. Okay. So this is the stress tensor for perfect fluid. I'll give you a derivation for this, but I'll have to see if I have time. If I have time at the end, then I will give you derivation for this. It's not that long, but I have to go through other things. But before I leave, this topic, there are certain things that I want to, say. One thing is that there is a simple expression that you can write down for perfect fluid. So the expression is as follows. Um, you can write down this expression. P naught G mu nu. Now, how do you get this expression? Well, the way to get this expression is to notice the following thing. So if you start like this, right? By the way, I didn't mention that this is in the rest frame of perfect fluid. So perfect fluid in the rest frame of fluid. Yeah. Yeah. You can write this down as follows. Minus P. I'll just write the diagonal entries now to save time. Plus I'm sorry, I think that there is some mistake here. Give me a minute. Sorry, this is 0. This is 0. So you can write down this matrix as these two contributions, right? Now, the thing is that this first matrix is nothing but P naught times eta mu nu, because eta mu nu has a negative entry in the time component and then it has positive entries. This is rho naught plus P naught times this, but in the rest frame. So I told you that in the rest frame, we have this, right? So it means that if you calculate this thing in the rest frame, you will get a non-zero entry only when mu and nu are both zero, which is the first, entry. Okay. So it means that in the rest frame, T mu nu equals, their sum, which is this thing. Now, if you want to generalize this particular expression to arbitrary coordinate systems, then this won't change. I mean, this has the same form in arbitrary coordinate systems, but this will change because you don't have the flat metric in any coordinate system. So you will have to change this to G mu nu. And this is the expression for the stress tensor of a perfect fluid in arbitrary coordinate systems, right? So that's one of the expressions that we will, need very, very heavily in the future. But before I proceed, let me know if there are some questions. The particles are in random motion in a perfect fluid, then how do we define the rest frame? There is a rest frame of a perfect fluid because, for example, you can define the center of mass of that, of those of those particles, and then there is a rest frame of the perfect fluid. I always get a bit confused. Is there any condition for when we can take a locally flat equation to curved spaces? So if you can write down an equation in covariant form, then you can the thing is that what does the word covariant mean? Covariant means that it transforms as a tensor. So if you know the form of an equation in a locally flat space time, locally flat space, locally flat coordinate system actually, and if it's written in a covariant form, you can write down that equation in arbitrary coordinate system because the form of that equation has to be the same, right? And let me know if this definition of manifold implies locally flat. Well, Riemannian manifolds, I mean, you can actually show that you can always choose, coordinate systems around a point such that the metric tensor is flat and the first derivatives of the metric tensor vanish, but not the second derivatives, by the way. You cannot make them zero by coordinate redefinitions. But I don't think that it's coming from the definition of the manifold itself. You have to put the structure of a metric tensor on a manifold, and then you can show that you can always choose coordinates such that the metric tensor is flat and the first derivatives are zero. Okay, now let's play with this particular expression. Now we have this expression for the stress tensor, and I showed you that the stress tensor has to satisfy the conservation equation, right? What does that imply for us? So we saw that you must have this thing equal to zero, right? Um, what does that imply if you use this expression for the stress tensor? Well, let's see. So you get this thing. That that's that the I'm sorry that the pressure and the energy density, they don't have to be constant, so they can have a non-zero derivative, so be careful about that. Now you have this equation. It turns out that you can write down two equations coming out of this equation, and I can tell you how to do that. But if I do every step, then I'll take a lot of time, so I'll just tell you how to derive those equations. You can fill in the details. So if you take this equation, right, and you multiply it with, so there's a one free index, which is nu. Multiply this equation with nu, u nu. You will get this equation. By the way, I have to remind you of something. So you have to remember that the for velocity, when you contracted with itself, it gives you -1, right? If you take the derivative of this equation, you will get 0 because -1's derivative is 0. But you can simplify that equation to show that this has to be 0, right? So there are two equations that you will need. One of them is written here, and the other one is this. So use these equations, okay? If you use these two equations and you multiply this black expression with u nu, then you get this equation that I'm going to write down. Now, you may not recognize what this equation is, but we will come back to this equation. So let's call this equation 1. The other equation that you can derive is if you take 1 and multiply that with u nu, right? Sorry, let's call this equation 2. Let's call this equation 1 without this u nu. Okay. So you take equation 1 and subtract 2 after multiplying u nu. Okay. Then you get this other equation. It's simple algebra. It's nothing complicated. That's why I'm glossing over it. But let me know if you have some problems deriving it in the next lecture, for example. Right. So let me make some space for this. Yeah. Let me call this equation 3. So we get two equations, equation 2 and equation 3 from equation 1. Now equation 1 came from the conservation of the stress tensor. Now, what are these two equations, equation 2 and equation 3? Are they familiar? I mean, have we ever seen them before? Well, we can actually see what these equations mean if we come to a limit where energy dominates, an energy dominates pressure, right? So if you come to, which is a non-relativistic limit, by the way. So if you come to a limit where energy is much, much bigger than pressure, right? Yeah. So where rho naught is much, much bigger than a pressure, it means that you can drop pressure terms in comparison to energy terms, right? So let's take equation 2, for example. Equation 2 says, this is equation 2. Now, the first term has a derivative, a factor of u, and a factor of rho. The second term has a derivative and a factor of u and a factor of pressure. But now you can see that the difference between the two terms is that one of them has rho and the other one has pressure. So it means that in this limit, you can just drop this second term, right? And then you get this. But what is this? I mean, if you write this down, in detail, you get this equation. So I means that it's a space component. It's 0. In the non-relativistic limit, if I write down u again, I told you earlier that it's equal to this thing, gamma and gamma times velocity. In the non-relativistic limit, gamma just goes to 1. And therefore you get this, right? It means that this equation becomes equal to 0. Now, this is also referred to. So if you remember from, physics 1, for example, you would remember that energy density times velocity is also referred to as current, energy current, right? So you can write this as J, right? And this becomes, so this I structure that's appearing, you can write that down like this. And you can see that you have attained the continuity equation. So it means that equation 2, which was unfamiliar in this form, if you bring it to its non-relativistic limit, it just gives you the continuity equation. Okay, that's good to know. Let's talk about this equation 3. Let me just copy it. Let's see what this gives you in the non-relativistic limit. Okay, so if you again drop pressure terms in comparison to the rho terms, this term should go away, right? So just get rid of this term. What about the other terms? Let's see. So the other terms give you this thing. Wait, yeah, I think so. This equation has a free index called nu. Let's confine ourselves to the spatial component only. So let's take v equals I. Mm, I. Okay, good. Now what does it give you? It gives you the following. So if you sum over the mu thing, that gives you t. Sorry, t plus let's call it j. Sorry, j. Mine equals minus. Now this is a flat matrix, so it means that mu also has to be I as well. And I'm bringing this inside to multiply with both terms. U mu, okay, U T. Wait 1 minute. Yeah, I think I need to drop this term. Yes. So if you look at these two terms, look at this term and look at the term that you will get if you multiply this with this. Well, here you have a derivative, u I and u mu, and you have rho. Here you have ui, u mu, a derivative and pressure. So it means that unit-wise, magnitude-wise, the only difference is between, rho naught and pressure. So it means that you can drop the term that you will get if you multiply these two terms. Okay, so that's why I will not write that term. So the only term that comes is this one, and let me bring it here. Now let's write this equation in a more, uh, familiar form. So I told you earlier that ui is just velocity. So and ut becomes 1 in the non-relativistic limit. So this is just velocity. Now this sum over j can be written as follows. This is v dot nabla applied on vi. And this is nothing but, uh, nabla I p, because this is just, 1, as we know that the spatial components of the metric tensor is just 1. Okay, so if I write this in a vector notation and in a more simple form, this becomes this, right? Now, I don't know if you have seen this equation before, but if you have learned fluid dynamics, this equation is sometimes referred to as the Euler equation of motion. So this comes from fluid dynamics. So Euler equation of motion. This combination that you're seeing here is sometimes referred to as the convective derivative, and it is also written like this, capital D and capital D. So you can write down this equation as this. So this equation, as I told you, that it's called Euler equation. It means that in the non-relativistic limit, we have recovered something that we already knew before relativity was even a thing, right? So it means that the equations that you are getting from the conservation of the stress tensor of a perfect fluid are giving you equations in the non-relativistic limit that you already know. That's known physics. One equation gave you the continuity equation, which is here, and the other equation gave you the Euler equation of motion, right? So it means
Yes, I think there's a network issue from his end. Just wait 5 minutes, and then Hassaan, can you? Okay.
Got two equations. Yeah, so I was saying that we got two equations from the conservation of the stress tensor. One of them is called, the continuity equation, which we already know. And the other one is the Euler equation that if you have learned fluid dynamics, you would know about that equation. Okay, now there is one more thing that I need to mention, but I won't go into the details because that's one of the problems in the problem set, and you will explore that particular topic in the problem sets. And the topic is energy conditions. So energy conditions are a particular set of conditions that you put on, energies that you are getting in your theory. For example, we have talked about these parameters like rho and pressure. You can ask the question that can rho ever be negative, for example? That will be a problem. I mean, if rho or the energy density is negative, that's a problem. If can pressure be negative or is the pressure always positive? Well, you will explore what happens that when pressure is negative and if pressure is positive. So there are certain kinds of energy conditions. One of them is called the weak energy condition or weak energy condition. One of them is called the, null energy condition. And there's another one called the strong energy condition, right? There's one more that is called the dominant energy condition, but I'm not going to talk about that. So these energy conditions put certain constraints on pressure and energy density, and you will see what each energy condition gives you, as a constraint in the problem set that you will get. These energy conditions are important because some of the theorems that people prove in general relativity use one of these conditions many a times. Actually, sometimes many theorems actually use strong energy condition, for example. Okay, so I just wanted to mention that so that you would know that this is coming when you go to your problem sets. Okay, now let's come to the big task of constructing Einstein field equations, and we have 40 minutes, 43 minutes to do that. Okay, good to know. So in the beginning, I said that the Einstein field equation should have a geometry side. Sorry. And you have a matter side. But now, since we have learned that the source of gravity is actually energy and not just mass, so let me call it energy side, right? Now, what is the candidate for the energy side? Well, we have seen from the last 1.5 hour that we have spent on stress energy tensor that the thing that should appear on the energy side should be stress energy tensor, right? So it means that it's not hard to guess that this side should be T mu nu, and you may have a proportionality constant that we will refer to as kappa, right? We don't know what kappa is. We will determine what kappa is in the next lecture. But let's not go into what kappa is right now. What about the geometry side? Well, that's not too simple actually. So there are multiple, candidates that you can have here. For example, one thing that you know, sorry, one thing that you know is that since T mu nu is symmetric, as we discussed earlier, the geometry side should be symmetric as well, right? Okay. So that thing gives you many different candidates. One of them can be just the metric tensor. The other one, the Ricci tensor, for example. Sorry. The other one is the Ricci tensor, right? Both of them are symmetric. I mean, if you exchange mu and nu in the metric tensor, it doesn't change, right? The same is the case for the Ricci tensor. Well, does any of them work? Well, let's see. Let's start with the metric tensor. I'm sorry. Yeah. Let's start with the metric tensor. Let's call it guess one, the metric tensor. right? Now, if we use our physical intuition and we say that suppose that there is a case where space time has no matter, no energy, no momentum whatsoever in it, that would mean that you have a vacuum, right? So, vacuum means that there is no energy, no mass, no momentum in it, which means that T mu nu is zero, right? In this particular scenario, you expect the space time to be flat, right? Which means that you have a flat metric tensor. So you expect that G mu nu is just eta mu nu, which is the space time, right? But is that what you get from this guess? Well, of course not, because if G mu nu is equal to kappa times T mu nu, and if T mu nu is zero, that means that G mu nu is zero. It's not just not what you expect, it's actually pretty bad because metric tensor cannot be zero. That's like a degenerate metric tensor. So that's a big problem, which means that guess one is wrong. Okay. Now, what about the other guess that we mentioned? Guess two. Let's try R mu nu equals kappa T mu nu, right? Now, what about this guess? I mean, does it give you what we expect? Well, first of all, I think that you may have gone through this, but you know that the Ricci tensor is symmetric, right? Can somebody say in the chat if you know that the Ricci tensor is symmetric? Why that I'm okay, good to know. So you know the Ricci tensor is symmetric. So this is good to know. What about the fact that if T mu nu is zero, then you should have flat space time at least as a solution? Well, sure, let's see. So if T mu nu is zero, that means that the Ricci tensor is zero. Okay. Well, the Ricci tensor is zero doesn't necessarily mean that the space time is flat, but at least flat space time is a solution of Ricci tensor being zero. So because we know that if you have flat space time, sorry, it doesn't necessarily imply that the Ricci tensor is zero. It implies that the Riemann tensor is zero, right? If the Riemann tensor is zero, that implies that the Ricci tensor is zero. So it means that if Ricci tensor is zero, that makes it possible for the space-time to be flat. It makes it possible, but it doesn't necessarily imply that the space-time is flat. Okay? Actually, there are a whole bunch of manifolds which are very interesting, and they are nowhere. There are nothing, anything, flat. Sorry, there's nothing flat about them, which are called the Ricci flat manifolds, right? And they are, for example, used in string theory research as well, like Calabi-Yau manifolds and things like that. So Ricci tensor being zero definitely doesn't imply that the spacetime is flat, but at least flat spacetime is possible if Ricci tensor is, So there is no obvious flaw in this equation. Okay, so probably this guess is true, but not so fast because there is another problem with this guess. So if you write this equation again, R mu nu equals kappa T mu nu, we do know that T mu nu has this conservation law, right? It means that if I put this thing, sorry, let me just write it like this. So if I put this thing on both sides, we do know that this is zero, right? If this is not zero, that's a problem. And if it is zero, then we don't have a problem, right? So is this zero? Well, that's one of the homework problems that you are going to do. You're going to show that R mu nu is actually not zero, but if you take this particular combination that I'm writing here, that's zero, where R is just the Ricci scalar defined like this. Okay, so that's one of the homework problems. For that, you would need the Bianchi identity. Sorry. Yes, it has to do with Bianchi identity. Someone asked the question. Yes. And mu, alpha, beta. Okay. And this has to be 0. So if you use this Bianchi identity and contract some indices, I mean, you will have to figure out which indices to contract because that's a good exercise to do. Then you will be able to show that this property of this particular quantity is true, right? Which means that the Ricci tensor itself doesn't have a non-zero covariant derivative, right? But if you add this quantity minus 1 over 2 r g mu nu, that has a zero contraction with the covariant derivative, okay? So it means that this thing is non-zero, which means that guess 2 is wrong. But since we explored guess 2, we have got a new guess now, and that guess doesn't have any, you know, obvious flaws. So let's talk about guess 3. And guess 3 is, as you surely know, is this one. Kappa times T mu nu. Now, as you can see, that this side is symmetric, right? This side is, well, if T mu nu is 0, then this side allows flat space-time. And this side has, a zero covariant, a contraction with the covariant derivative. So this doesn't have any obvious flaws, right? Now, this equation turns out to be true in reality because this is called the Einstein equation. This equation has been tested, I mean, with the value of kappa that we will derive later, has been tested multiple times, and it is the famous Einstein's field equation. Field equation. EFE. So we have found the right candidate for, connecting geometry with angular moment, with a stress energy tensor, right? Now, the thing is that there are some modifications that you can do to this equation, and I will talk about those modifications, and I think that's the last thing that I will, say today. Let me go through them. One thing is the following. If T mu nu is 0, does that still imply that R mu nu is 0? Well, actually, yes, as you can easily see, if T mu nu is 0, you will get this thing, right? But it doesn't necessarily imply that R mu nu is 0, right? But the thing is that it does. If you contract this equation with G mu nu, right, on both sides, the other side is still 0, of course, that gives you R minus 1 over 2 R G mu nu contracting with G mu nu, but you know that in 4 dimensions it's 4, right? So therefore you get 4 equal to 0. That gives you, after some simplification, that R equals 0. But if R equals 0, then this equation equal to 0 implies that R mu nu equals 0. So it means that this thing is still true. That if T mu nu is 0, then R mu nu is 0. So it's exactly like guess 2, although, we are not doing guess 2 now. There is one more thing that I need to mention, actually two more things, then we can, start taking questions. Also, yeah, I know, cosmological constant. I'm going to come to that. That's one of the things that I want to talk about. So yeah. So there's a question which says that a lot of research papers have cosmological constant. Yes, that's one of the things that I'm going to talk about. But there is one more important thing that I'm going to talk about before that. So as you surely have heard before, Einstein field equations, they are very beautiful. Of course, that's one of the pinnacles of human understanding. But solving them is not that easy. If you solve these equations, what are you solving for? Well, if T mu nu is given to you are solving for the metric tensor. Sure. But you can see that, R mu nu is a horrible combination of metric tensor. I mean, the metric tensor and its derivatives, actually. And the same thing goes for R. So we want this equation to be as as less horrible as possible. And in this form that I have written it here, it's quite horrible. I mean, if you write this equation down in terms of the metric tensor, it's going to be a very horrible different set of differential equations. So you can make it less horrible by replacing r with another value, sorry, with another quantity. So let's start with this equation again, kappa times t mu nu, and contract both sides with the metric tensor. If you contract both sides with the metric tensor, you will get r minus 1 over 2. So contract with the metric tensor, you will get 4 equals kappa. And here you get g mu nu contracted with t mu nu. This is referred to as capital T, right? So this left side will become minus 2, sorry, r minus 2r, but that's just minus r. So minus r equals kappa times t. That implies that r equals minus kappa times t. Now you can replace r here with this equation that you get here. Okay, if you do that, that becomes minus kappa times t, g mu nu equals kappa times t mu nu. But since this term has, sorry, since this term has t in it, you can take it on the other side. If you do that, that becomes r mu nu equals kappa times t mu nu minus 1 over 2 kappa, sorry, not kappa, t, or g mu nu t. This equation is less horrible as compared to the equation that I wrote before, because this doesn't have the Ricci scalar. You still have Ricci tensor. I mean, you cannot get rid of that at least, but you at least got rid of the Ricci scalar, right? And this equation is sometimes referred to as the trace reversed form of Einstein's field equations. When physicists solve Einstein's field equations, they use this form because this is easier to solve as compared to, the original form of the Einstein field equations. And from this equation, you can easily see that if T mu nu is 0, then R mu nu has to be 0. Because if T mu nu is 0, it implies that T is 0 because that's just the contraction of T mu nu with, G mu nu. And that would imply that this left-hand side is 0. Sorry, imply that right-hand side is 0, which means that R mu nu is also 0. So if this is 0, if this is 0, then R mu nu has to be 0, of course. Okay, so that's one thing. The other thing is the cosmological constant. So the thing is that if you write down, I'm going to write down the original form of the Einstein field equations again. Kappa, I'm going to make some room here. Okay. Now, if you remember our argument, if you recall our argument from some minutes ago, you would remember that we wrote down this combination here because if you contract this combination with, nabla mu, this gives you 0, right? Which is the same as if you contract, t mu nu with nabla, right? That also gives you 0. Okay. But the thing is this the only combination that you can write down that gives you 0 when you hit it with nabla? Well, not really. If you remember, from your previous lectures, I'm sure that you have gone over this. If you take the covariant derivative of the metric tensor, what does it give you? Well, it gives you 0, right? And you can multiply both sides with a constant, and that still doesn't, this equation still doesn't change, of course. And I'm going to write down that constant as lambda, capital lambda, capital lambda. You can multiply lambda on both sides. Yeah, I think that's true. I think that's true. I'm not going to use my video, so I can just charge it using my laptop, I guess. Give me a minute. Yeah, I think I'm fine now. Oh, 1 minute. Okay. So I can multiply both sides with lambda, right? Okay. The thing is that since this is a constant, I can bring it inside and I can write this down. Sorry. Okay. So it means that we have another combination whose covariant derivative is 0. And therefore, if you write that particular term on the left-hand side, that still doesn't change the fact that if you hit the left-hand side with nebula, you will still get 0, right? It means that this term is allowed, this term. And this term is called the cosmological constant term, I'm sorry. Toot. Okay, cosmological constant term. Okay, so this term is used whenever you want, an anti-gravity type of effect. This term was used by Einstein to balance the universe from expanding. I mean, when he solved his equations actually told him, as we will see later, that you cannot have a static universe. And he added this term to, have a static universe, and then he called it, the biggest blunder of his life. But this term is there because it doesn't change the covariant derivative of the left-hand side, and it is still 0. A very important thing to notice here is this step that I did. This step. This step was possible only because lambda is a constant. If lambda was not a constant, I would not be able to bring it inside, right? It means that cosmological constant has to be a constant. It cannot depend on the position or time. So when people talk about time dependent cosmological constants, they're not actually saying time dependent cosmological constants. They mean that you get an effect which will be because of something called like time dependent cosmological constants, but those effects are you know achieved by something like quintessence, for example. But cosmological constant has to be a constant, otherwise you would have a problem on the left hand side, because then you would not have a non-zero nebula. Okay, unless the covariant derivative of nebula of lambda is 0. That's the only way to achieve this. Okay. Uh, Now, one one thing that we still need to figure out is that what is kappa? I mean, we still don't know what kappa is. Until we don't know that, we cannot use this equation to start making predictions about the universe. Well, how do you determine kappa? Well, you have to determine kappa by connecting this particular equation to known physics. How do you do that? Well, what we will do is that we will try to derive Newton's gravity using Einstein's equation and see that what is the value of kappa that will allow us to, connect Einstein's field equation to Newton's gravity. And we need a particular tool for doing this. It's called weak field approximation or weak field limit that we will cover in the next lecture. But that limit is useful not just to determine kappa, but to study many other things like gravitational waves, which we will not cover in this course, I think. But I will give you this tools required to deal with most of the things which are used in gravitational waves, for example. Okay, so I think I'm done. If there is any question, let me know. If there are no questions, I can explain another topic. I mean, a small topic. Hmm. Let's see. Can you suggest some readings for this topic? Yeah, I mean, there are, for example, you can read Sean Carroll's book. I mean, I have a favorite book on general relativity, which is Thomas More's A General Relativity Workbook. I just love that book. So you can read that. But there are many, readings that you can have. I mean, Sean Carroll's book is there. Hobson's book is there, right? Yeah, I think these are the things that come to mind. I mean, Weinberg's book is there, but it takes some time to read. What resources should we use to study today's stuff? I mean, I've answered that. As I see, the cosmological constant make that Ricci tensor doesn't vanish if that's true. Well, that's true, yes. So if yeah, you're right. But the thing is that another topic that I'm going to explain. So the question is that, as I see, the cosmological constant makes that Ricci tensor doesn't vanish if t is 0. You're right. If this t that I've written here is not zero. So if it's zero, that doesn't necessarily imply that, Ricci tensor is zero. But one topic that I'm gonna, explain later is that you can see cosmological constant as a contribution to the stress tensor. So if the total stress tensor vanishes, then Ricci tensor vanishes still. Okay. Is the cosmological constant still relevant? Well, until now, yeah. But let's see how experiments fold out in the future. Okay. Can you suggest some? Yeah. Okay. I think there are not a lot of questions, so I can, discuss one more topic before we leave. So cosmological constant looks like a symmetry of the equation. I don't know what symmetry you're referring to. I don't know. But what is the conserved quant? I don't know what you're referring to here. I mean, cosmological constant is a constant. It's not. It cannot be a symmetry. But there is a very interesting question which says that. So there was a time when people used to think that cosmological constant is zero. Before we discovered that the universe is expanding. At that time, people used to think that the reason that cosmological constant is zero is because of a symmetry, right? Um, so that's the only connection that I can see between a symmetry and cosmological constant. But the fact that cosmological constant is small is still unexplained. I mean, and that's probably one of the biggest problems in physics, right? Okay, I can explain one more topic before we end this. So now we have this equation with cosmological constant. I can do the same thing that I did earlier. So when I wrote down the Einstein field equation, I wrote down its trace reversed form like this, right? I can do the same thing with cosmological constant. Sorry, with the equation with cosmological constant. So let's contract both sides with a metric. That will give you, sorry, that will give you R minus 1 over 2 R 4 plus cosmological constant times 4 equals to kappa times T. That will give you R minus 2R, but that's just minus R, sorry, minus R plus 4 lambda equals kappa times T. And that will give you R equals 4 lambda minus kappa T. Okay, so if you use this expression, plus, right, then you will get this thing. So take everything on the other side. Um, sorry, sorry. Let me do another step. Sorry. And this thing. Now you can see that you have these two terms, this term and this term. They will, simplify to give you minus lambda g mu nu. And that will give you minus lambda g mu nu. Okay. Now, if you take it on the other side, it will give you this thing. T mu nu minus T over 2 g mu nu. And then plus lambda over kappa g mu nu, right? Now you can ask the question that is there some stress tensor, let's call it T mu nu, right? T tilde mu nu, such that if you if you calculate this particular quantity, right, that will give you this. Because if there is such a stress tensor, then, I mean, and the thing is that you can actually find out what the stress tensor is. If there is such a stress tensor, then you can write down this equation as follows. Kappa T mu nu plus T tilde mu nu minus T plus T tilde over over 2 G mu nu, because I wrote down this thing as this thing. Okay. So that will give you kappa times T total mu nu minus T total over 2, or let me write it down like this, G mu nu. And that's a way to see that the stress, that the cosmological constant actually gives you a stress tensor that contributes to the total stress tensor and gives you, something that looks like the trace reversed form of the Einstein's field equation, which is given here. The only thing that changes is the stress tensor. So how to find this stress tensor? Well, it's actually not that hard to find actually. You can start by saying that, okay, so suppose that T mu nu is like zeta. Zeta is just an undetermined number times T mu nu, oh, sorry, G mu nu. Then it means that this thing has to be 4 times zeta, because if you contract the metric tensor with itself, that will give you 4. Okay, so T mu nu tilde minus 1 over 2 T tilde G mu nu becomes zeta G mu nu minus 1 over 2 4 zeta G mu nu, and that gives you, well, minus zeta G mu nu. Now we wanted it to be this, lambda over kappa G mu nu, lambda over kappa G mu nu, which implies that zeta is minus lambda over kappa, which means that the stress tensor that we were looking for is this, minus lambda over kappa G mu nu. So you can see that the stress tensor, that the cosmological constant contributes an additional stress tensor into the picture. So earlier there was a question that I see that the cosmological constant implies that the Ricci tensor doesn't vanish if t is 0. You're partially correct. If you want the total stress tensor to be 0, then Ricci tensor is still 0. Okay. But if you say that, no, only this stress tensor is 0, not the one that comes from the cosmological constant, yeah, then the Ricci tensor doesn't have to be 0, of course. But you can see that the cosmological constant itself is a contribution to the total stress tensor. Okay. Okay. Let's see how much time do we have. We have like 13 minutes. Okay, so in these 13 minutes, if there are no questions, I can try to derive what I promised earlier. So earlier I promised that I will derive the stress tensor of a perfect fluid, which is something like this. So I can do that, but if there are some questions, I can answer them. So let's see if there are some questions. No? Okay. Then I can tell you how to derive these. Sorry. Wait, I think I have some problems here. Okay. Okay. So how to derive the stress tensor? Well, the way to do it is to start with a cube again, as we did for the dust. All right. And for the fluid, first of all, this cube again has length L, right? And this cube is in the rest frame of the fluid. So that's very important. Sorry, rest frame of fluid, right? As I told you earlier, that a fluid is made up of particles which are in random motion with respect to each other, but they're still not interacting. So what you can do is that you can divide this fluid into many different parts. And in each part, you have particles that move with a particular force velocity, right? So let's talk about such a subset. So if you have like many particles like this, you can divide them with respect to what force velocity they move with, right? And if you consider one of these subsets, it's easy to see that each of these subsets must be dust. Why? Well, because since they move with the same force velocity, they must be at rest with respect to each other. Okay. So it means that each of these subsets is dust. Therefore, the T mu nu of each of these subsets, let me call it, well, okay, let me call it subset T mu nu is what we had earlier, right? So rho naught is the, energy density in dust's rest frame, and you know what u mu and u nu are. They are just the four velocities of the particles. Now what we need to do is that we need to write this down in terms of something that relates to the fluid rest frame, right? So what is rho naught? Well, rho naught is the number density of the uh, number density in fluids in the dust's rest frame times mass, something like this. Well, the thing is that you can write this down as, this is number density in the fluid's rest frame. So this is number density, not in fluid's rest frame, in dust's frame, right? So this is, as we saw earlier, equal to this thing. Now this is number density in fluid's rest frame, right? So you can, if you use this particular equation, you can see that this stress tensor that we wrote earlier is this. So rho naught, something like this. If you multiply multiply and divide with m squared, you get something like this. M divided by m squared. And these things are for momentum, right? So you get rho naught times something like this divided by m squared. And if I'm not wrong, I think you can write this down as, n divided by ut m. So I just wrote down the expression for rho naught times p mu divided by m squared. So these steps are really important. That's why I'm doing every step. N times p mu divided by. So you can see that one m cancels, and ut times m just becomes pt. Right. Okay. So it means that stress tensor for the subset, that's very important, subset, equals n times p mu over pt. Now, n is, as I told you earlier, is the number density in fluids frame, right? So which means this cube, right? And the number density is just n over L cubed, because this L is in the, this length L is in the fluids rest frame, not in the dust's rest frame. That's very important to know. Okay, so it means that you just have n over L cubed p nu over pt. Okay, now this stress tensor is only for the subset. Okay, now if you want the total stress tensor for the whole fluid, you have to integrate over all different momenta, because this stress tensor is only for a particular forward velocity, which means a particular forward momentum. So the full stress tensor for the fluid is nothing but n over L p mu over pt, and n now depends on the momentum, and you integrate over all the momenta. This d3p means that you are integrating over px, py, and pz. Okay. Now, this is the stress tensor that we wanted to calculate, but we want to write it in terms of something that we understand, better. So you can see that the L cubed is just a constant, so you can take it out. Okay, and then you get this thing. Now, before I proceed, I need to remind you that fluid has random motions. What does that mean? It means that if you can, there is no preferred direction for the motion, right? It means that if you have number of particles for p, that should be equal to, sorry, number of particles for negative of p. So that's a very important thing, because if you don't have this thing, then you won't be able to derive what I'm going to derive later, right? Sorry. Okay. Now, let me show you first, because there was a question earlier that how do we know that the stress tensor is diagonal? Let me prove that it has to be diagonal. So first of all, let's write down Tx, for example, or like 0, 1. Yeah. 1 over L cubed. So 0, let me write this T as 0. Yeah. 1 divided by 0. Now you can see that this cancels, right? So you get 1 over L cubed P1. But you can see that this integral has to be 0. Why? Well, because if you, so P is just an integration variable. I mean, the momentum. If you send P to minus P, this integral becomes, well, this integral should not change if you send P to minus P, because P is just, an integration variable. So this, and this becomes this, right? But as we have seen that this should be equal to NP, you get this minus sign that comes in the start, and you get minus L cubed, like this. So it means that this integral is just negative of itself, which means that it should be 0. So it means that T01 is 0. And similarly, you can show that T02 and T03 are 0, right? If you use a similar argument, you can show that if you take ij, okay, let me take specific cases like 1, 2, for example. That will give you P1, P2 over P0, right? But you can again see that, this integral should be 0. Because if I just change the sign of P1 only, right, or P2 only, this integral goes to negative of itself, right? So if I just say that P1 goes to minus P1, well, this integral again gets a minus sign, for example, from here, right? And you again get, a negative of your itself, which means that this integral vanishes. So the argument goes like, so there's an question which says that can you argue further why NP is equal to N of minus P? Because the motions are random. If the motions, if NP is not equal to N of minus P, it means that in one direction is preferred over the other direction. So if momentum is in one direction, that has more particles that as compared to the number of particles for the momentum that is opposite of that momentum, of the earlier momentum, right? So that's not random. That's why I said earlier that random is a very important thing in the definition of perfect fluid. Okay. So similarly, you can show that T12 is 0, which means that you can use the same argument to show that T13, T23, T 2 4, sorry, not 2 4, 3 4, sorry, 1 2 2 3. I think and that's it, right? 1 2 1 3 2 3. Yeah, they're also 0, because in the other ones are just symmetric, so that's not a problem. So you can see that why this thing is diagonal. The stress tensor, if you write it down like this, you have shown that these are 0. These we don't know, but these are 0. This we don't know, but this is also 0. Right? So now we have shown that the stress tensor has to be diagonal. So that's one thing. Now we will show that these three entries are actually equal. How will you show that? Well, let's calculate one of them. So T11 equals 1 over L cubed P1 squared over P naught. How will you show that this is related to something like pressure? Because we know that here you have pressure. Let me try to argue that. I don't know if I have enough time to do that, but let me try to argue. So suppose that you have a cube, right? Length L, of course, right? Now suppose that there's a single particle in this cube, right? What is the pressure due to that particle? Well, the pressure due to that particle, what is pressure, first of all? Pressure is force divided by area, of course, right? So what is force? So suppose that particle comes here, with the velocity VE, for example, or momentum px, yeah, and it goes back because it has an elastic collision, and it has momentum minus px, right? So force is change in momentum divided by change in time. That's the relationship between force and change in momentum. So it means that the force is change in momentum, which is 2 times px divided by change in time. Okay, if you use that, then pressure is 2 times px divided by change in time, right? And then divide by area. Now area is just L squared because this is the area that I'm talking about, right? Okay, so you have 2 times px over delta L, delta t L square. Now, what is delta t? Well, what is the time difference between two collisions? Well, it is the time that it takes for it to come from here to here and then go back, right? Um, yes. So delta t is 2 times L divided by the velocity of the particle, which means that it is 2 times L times m Vx times m, which is just 2 uh, Lm over Px. So the pressure becomes, wait 1 minute. Yes, the pressure becomes 2Px divided by delta T, sorry, L squared. Delta T is 2Lm times divided by delta P. So you get another delta, sorry, Px here, and you get Px squared over L cubed M, something like that. So I think I'm running out of time, but let me just show you that you have this factor, P squared over L cubed, and that appears. So which P1 is just Px, right? So you have Px squared over L cubed, and this P0 is related to this M that you have here, right? And you have to integrate over all such particles to get the total pressure. I think I'm rushing into the argument, so I will include this argument in one of your problem sets so that you can understand this argument better. But I have told you the gist of the argument, that this is how you derive, the stress tensor, and then show that this is nothing but, the pressure that you have in the x direction, right? Using this kind of argument that I have given you here, right? Now, the thing is that since there is no preferred direction, there is no reason why pressure in x direction should be different from pressure in y direction, and there should be no reason why that should be different from the z direction, which means that if T11 is P in the x direction, T22 is pressure in the y direction, and T33 is pressure in the z direction. Because of the fact that the motions are random, these three should be equal, which means that T11 should be equal to T22 should be equal to T33. And therefore, these three entries in the stress tensor are just pressures. Right? What about the first one? Well, it's not that difficult. It's not that different. It's pretty similar actually. So T00 is just 1 over L cubed, just using the previous expression. N P P naught over P naught. Well, that just cancels. So you just get this thing. This is nothing but the energy of a particular particle with a momentum P, and you just integrate over all of the momentum, all of the momenta. Sorry, yeah, all of the momenta. And if you bring in L cubed here, this is the energy density due to a set of a particular particle with momentum P. And if you integrate over all, momenta, you just get energy density, the total energy density. Therefore, T naught naught is again rho. Therefore, this should be rho naught. So I've tried to give you, a rushed definition, a rushed derivation for why the stress tensor of the perfect fluid should be what we had earlier. I know that I have rushed through the derivation, so there may be some points that you didn't understand. So I can include this problem in your problem sets. It was not originally there, but still, if you have some questions, I can answer them and then we can wrap it up. Can we argue that since this dust system is random, there can't be a preferred direction, so the non-degenerate spatial components will all be the... what do you mean by non-degenerate? You mean non-diagonal? I don't understand what you mean by non-degenerate spatial components, but what you are referring to is relevant. So since the motions are random, that's the reason why all of these diagonal components, the spatial diagonal components, should be equal, because the pressure in x direction, the pressure in y direction, and the pressure in z direction should all be equal. So yeah. Any other question? I think my tablet is about to die, but it's fine. Any other question? No? Okay. I think then we're done if there are no other questions.
Okay, thank you, Hassaan. Thank you very much. So I'll turn off the